Hello everybody, back on Packet Tracer today because we are now going through the version 6 bridging material for the CCNA routing and switching. This is going to be material included in the new curriculum under the version 6. I've just managed to recently attain my CCNA routing and switching certification under the version 5. Which is currently being outphased. I believe the last time to sit that exam is potentially the end of this month, I believe. I can't remember really, but we do know that this year from September the version 6 CCNA routing and switching is the new version, new curriculum, and there's a lot of new topics included, so I thought it'd be a good idea for myself to go through the bridging material and see what's new, and just kind of reinforce that knowledge that I've already got, and go over a few things that I may have be a little bit rusty on. So this is the first lab given in the 6.0 bridging material on NetAcad, which I'm currently a part of. So we're going to just basically go through this lab, which is testing connectivity with TraceRoute. Okay, so as it says, the background of this, for those that are not following along or do not have access to this material, even though I believe it is free, this activity is designed to help troubleshoot network connectivity issues using the commands and trace the routes from source to destination. You are required to examine the outputs of the TraceRoute, which is the TraceRT, which is actually a Windows command, and the TraceRoute, which is an iOS command, as packets traverse the network and determine the cause of a network issue. After the issue is corrected, use the TraceRoute and the TraceRT, again Windows command, to verify the completion. So basically what we're doing is we're verifying end-to-end connectivity with TraceRoute using the iOS command TraceRoute and the TraceRT from the Windows syntax. So we're going to jump straight in, and we're going to start by following this all the way down. So step 1, so it says send a ping from one end of the network to the other end of the network. Okay, so we're going to click on PC1, open the command prompt, ping PC3 at this IP address, which is 10.1.0.2. What message is being displayed as a result of the ping? Okay, well, let's find out. So we'll start by clicking on that, and we'll go to desktop, command prompt, and there we go. So we're going to ping PC3 now, which is here, 10.1.0.2/24. Okay, so we're going to do a ping 10.1.0.2, and we are getting a response from 10.100.100.6 showing, we'll just do that again, showing destination host unreachable. So 10.100.100.6, well, where is this IP address? What device is this? Okay, so if we look at these subnets, we can see we've got the 10.0.0.0/24 network, which resides in here. Then beyond this, which is a serial link, we've got a /30. So we have basically 4 or 2 usable, should I say. So we've got we'll have 10, I'm guessing 10.100.100.1 on this link. Then on router B here, we should have 10.100.100.2. okay. Then 3 will be the broadcast. Then we've got a new subnet here, which is 4. So 10.100.100.4. So the first usable is going to be 10.100.100.5 here, I believe. Then we have, last but not least, 10.100.100.6 here. So this ping is actually getting to this serial interface on router C by the looks of it, and it's coming back with a destination host unreachable. So we've tried to ping PC3 at 10.102. This is replying to us here at this point saying that we can't get to 10.102. okay, we don't know what reason that is yet. So basically this destination host unreachable is saying we've received the ICMP echo request, then it's sending a reply back because it's not being able to get any further to reach the actual network from this point on here. So it's sending a response back to PC1 saying this is the issue that we've got here. Okay, so that's a good long-winded explanation of kind of what's going on just from doing step one. You know, we can kind of find out a lot, see what's going on a layered approach anyway from a layer 3 packets. So we'll move on to step 2 now, and it says trace the route from PC1 to determine where in the path connectivity fails. Okay, so I've pretty much already explained where in the path it looks like connectivity is failing, but for the purpose of this lab we're going to go ahead and we're going to continue with the steps. So we're going to go to step 2A, which is from the command prompt of PC1, which is what we're on, enter TraceRoute or TraceRT 10.102. okay, so we're just going to do that now. Okay, and it says when you receive the echo timed out message, press Ctrl C, which will cancel it. What was the first IP address listed in the TraceRT output, and what does this belong to? Okay, so we've got a request timeout now, so we're going to go ahead and stop that with the Ctrl and C. So what can we see from this information here? Let's just move it up a little bit. Okay, so it's asking us what was the first IP address listed in the TraceRT output. Well, the first IP address listed in the TraceRT output is displayed there. That's 10.0.0.254. So the first hop from PC1 is going to be router A. So this is going to be this interface, the ingress interface. So that's going to be more than likely that IP address, or is that IP address. So 10.0.0.254. Okay, so we've determined that. So we know that it belongs to router A. So observe the results of the TraceRT command. What is the last address reached with the TraceRT command? Okay, so it looks like the last address that we get in here is 10.100.106. Then we got the timeout, and again 10.100.106, and it's not getting beyond the 100.106. So if you remembered what I said earlier, judging by the subnets, we've determined now that the first hop ingress interface is 10.0.0.254. And what will happen is a TraceRoute will then hop to the next device, and it will again be the ingress interface of the next device. So we're looking at router B's interface connecting to router A, so that'll be 10.100.100.2. okay, then the next hop from router B it's going to jump to router C, and the ingress interface for that, judging by the subnets, is 10.100.104. so we've got 5 here. We should have 6 on router C. So it looks like that's the case. So 10.100.106. okay, so it's getting here, then we're getting times out, and it's not getting any further. Okay, so we kind of determine that by the ping with the destination host unreachable up here, because with the destination host unreachable, we know that the device actually receives the ICMP echo request. However, it drops it or sends a response back because it's basically not getting to where it needs to be going. Okay, so moving on. Step 3, we need to now correct the network problem. So we're going to compare the last address reached with the TraceRoute, which is 10.100.106, with the network addresses listed on the topology. The furthest device from the host 10.0.0.2, which is PC1, which we're on now, with an address in the network range found, is the point of failure. What devices have addresses configured for the network where the failure occurred? Okay, so we know that the failures occurred on router C, so it'd be worth checking the configurations. So we're going to do that by the looks of it. So we're going to click on router C, and then we're going to go to CLI tab, and we're going to check the status of the interfaces. Just before we do that, we'll just jump ahead a little bit. We're going to compare the IP addresses on the interfaces with the network addresses on the topology. Are any addresses incorrectly configured? Make the necessary changes to restore connectivity. Do not change the subnets. What is the solution? Okay, so we're going to have a look at that now. So we're going to click on the command line now, and it wants us to look at the status of the interfaces and also look at the IP addressing schemes to make sure that they're the same as those displayed on the topology. So what we're going to do, we could do that with one command. So we're just going to do a show run. Okay, and we need to look out for serial interfaces, which is what's connected to router C. So we'll ignore the gigabit Ethernet interfaces, and we'll just look at these two interfaces here. At the moment we don't know until we explore more where these or which serials connected where, but we could probably, by looking at this, the status isn't down because it's not say shut down, so we know that both statuses are up. Okay, 10.100.100.6, well, as we found out earlier on, /30, which is 252 as well, we found out that that's router C's interface here, so we know that that's the subnet for this one, so we know that serial 001 is now this link here connected. Okay, and looking then at serial 000, we know that now this one is this link here connected to router D. Also, we can see that the status isn't shut down because there's no shutdown displayed underneath it. There is also other commands you can use to actually take a look at that. But what we want to look at here is the IP address. We can see that the IP address is 10.100.117/30, which is a 252, which is correct. So we know that the subnet mask is fine, but let's have a look at the IP address. This doesn't seem to be right. We've got 10.100.117, and if we look at this subnet here, we can see 10.100.100.8. So we've only got two /30 as well. So we know that we've only got two usable. So the first usable is going to be .9. So let's say that this interface on router C is .9. And then we have .10, which is probably router D, which we could also check by jumping the command line. Okay, so 17.17 is incorrect because it doesn't fall within this subnet. Okay, so this is probably where the error is. Okay, so let's just have a look and see what he wants us to do next. So we've identified that we've got incorrect IP, or an incorrect IP address. It says make the necessary changes to restore connectivity, however do not change the subnet. So obviously the subnet's going to stay the same, so what we're going to do is we're going to make that change now. It's not telling us how to make that change, it just wants us to make that change, which is good. So we're going to jump on config T. And what interface was it? Serial 000, interface serial 000, and we're going to do a not IP address 10 100 100.17, wasn't it? 10 100, yeah, 10 100 100.17. Okay, so then if we just exit out of them, we do show IP interface serial 000. We can see that there isn't any IP address associated with that, and if we look at serial 0001 for the same one, we can see that the IP address is associated with that. So that's what we want to see for serial 000 as well. Okay, so now that we've removed the IP address, we can then go ahead and the serial interface again and input the IP address we believe it should be. So before we do that, in fact, let's make sure that the IP address on this interface here for router D is .10, what we believe it should be. So we'll do a show run, and we're just looking for the serial interface, which is there. So as you can see, I was right, 10 100 100.10. Okay, so we know that router C's interface is going to be 10 100 100.9/30. Okay, so we'll jump back on that command line, and where are we? So IP address 10 100 100.9 255 255 255 252. Okay, we know that the interface is already active, so we don't need to worry about that. So if we exit out of that and we do the same command to show the interface, now you can see that we have the IP address listed here. The line's up and the protocol's up as well, so we know that everything's looking all good there. Okay, so Control C out of that, and we'll just do a copy run start. Okay, now so we've made the necessary changes. We've not changed the subnet, that's the same, so everything should work now. So it wants us to move on to step 4, and from PC1 commands prompt we need to trace RT to the same destination 10102, which is PC3. So we're going to do that now. So we could just up arrow that, and it's actually got now to 10 100 100.10, which we know because we've checked is the ingress interface of router D. Then from router D, the next hop then is jump straight to the PC3. So the trace completed and everything's all good. So we know that end-to-end connectivity is now successful. So that completes step 4. So we're going to now look at part 2, which is compare TraceRT to TraceRoute command on a router. So we're going to click on router A, which is here, and we're going to go to command prompt, spread that out a little bit more. Then what's it want us to do? So we're going to do, instead of, you can see the syntax is slightly different. So whereas Windows uses TraceRT, the Cisco iOS uses TraceRoute. Okay, so we're going to just go in enable, then we'll do a TraceRoute to 10.102, which is PC3 again. And as we can see, it has completed successfully. So that answers part 2B. So we're going to compare now the output from the router's TraceRoute to the TraceRoute on the PC. So we'll see what's different about the IP addresses. So we'll leave that here for now, and I'll just get that one back open. Okay, and hopefully I'll just make it the same size so that we can compare a little better. Okay, so we can see that there is some slight differences in the fact that obviously this is PC1, so it's actually got to its gateway first, 10.0.0.254. Because we started at the router here, the next stop, you know, is, let's just move this here. Because we started at the router A, the next stop then is 10.100.100.2. Okay, so we know that that's this interface, the ingress interface here for that one, which that's obviously got the hop there as well. Then we have 10.100.1.6, so that's the same as that. Then we have, oops, in fact let's scroll down to the right one, there we go. So 10.100.100.6, so that's fine. And we also have 10.100.100.10 and then to the PC. So the only difference is the fact that obviously PC1 started within its LAN and that the router hasn't. Okay, so one additional hop basically. So noticeably different about the IP addresses. So that's what's different about the IP addresses. Okay. So now we're going to use an extended TraceRoute. So in addition to TraceRoute, Cisco iOS also includes extended TraceRoute. Extended TraceRoute allows the administrator to adjust minor TraceRoute operation parameters by asking simple questions. Okay, as part of the verification process, use the extended TraceRoute on router A to increase the number of ICMP packets TraceRoute sends to each hop. Okay, and it's got a little note saying, "Note: TraceRT on the Windows also allows the user to adjust a few aspects as though the use of command line through the use of command line options." Okay, so that's just kind of making you aware. So we're going to focus now on router A, doing the extended TraceRoute. Okay, so we're going to do, we'll follow what it says. So we'll enter TraceRoute and press enter. So now it's asking us for an IP address. So sorry, it's asking for the protocol. Sorry, jumping ahead there. So what we need to do is IP protocol. Then we're going to do the target IP address. So again, it's 10.1.0.2. Enter. Then the source IP address is the device that we're on, which is the router. So we're going to put the egress interface, which is 10.100.100.1. The numeric display is N. Then timeout we're going to keep as 3. Probe count will change to 5 as it says there. Time to live is the same, and we're going to keep that the same as well. Okay, so it says note the value displayed in the bracket is the default value. So that's pretty much saying that these brackets here are the default. Okay, if no values entered, that's what will be used. So you simply press enter if you want to use the default value. How many questions were answered with non-default values? Okay, so I'm guessing that's what we've changed. And how many ICM packets were sent by router A? So we've got the there we go. So probe count is 5. So yeah, as it says there, probe count specifies the number of ICMP packets to each hop by TraceRoute. A higher number of probes allows for more accurate average round trip of the time taken. So this is, you know, basically the time taken. Just try to run through these quickly because they're just you know, basic questions. Still on route A, run extended TraceRoute again, but this time change the timeout value to 7 seconds. Okay, so we'll do that again. IP target IP 10.102, 10.100, 100.1, numeric display, keep the same. What we're changing, sorry again, timeout value to 7 seconds, so there we go. Probe count, we'll just keep it as free, and we'll keep these the same as well. Okay, there we go. So we changed the timeout value to 7 seconds. What happened? How does the different timeout value affect the trace route? Okay. Can you think of a use for the timeout perimeters? So yeah, they're just basically questions at the end, as you can see there. We changed the where's it gone? Sorry, we changed the timeout in seconds to 7 seconds, whereas before it was 3 seconds. Okay, so you know, it's just basically that, you know, it does what it says on the tin really. It's just changing the timeout values, and you know, that's pretty much it. But yeah, that's, I believe that's pretty much all of that lab really. So thank you for watching. If you have any further questions, please do drop me a comment. But thanks for watching. Yep.